All right, we can start today's webinar now. So first of all, a warm welcome to everyone who joined. This is our first webinar of 2024. So I wish, on behalf of Diabetics, I wish you all a very happy new year. I hope you're not tired of hearing that. My name is Niels. I will be your host today. Apart from being your host, I'm also one of the customer support engineers at Diabetics. So that means if you have a technical question, or if you have a project or if you do a project with us, there's a very high chance that you will get in contact with me. That's enough about myself. Let's move on to today's topics, where we will tackle the thermal management early on in the design cycle by using fast concept generations. For today's webinar, I've laid out the following talking points. So first, of course, I will give an introduction to Diabetics for the ones who don't know us yet. We'll then move on to the importance of early thermal management. Basically, why should you care? Then we'll move on to applying that in practice. The theory behind concept generator, and then we'll apply it into practice by using two different case studies. After that, we'll have a Q&A session. So anytime you have a question, feel free to put them in the public or private chat boxes. Our moderators are following both. So if you have any question, our moderators will answer those. And any interesting questions or unanswered questions, I will cover towards the end. And lastly, if you want to try the software for your own, I will give some information on where you can do so. All right, let's move on to explaining a bit what Diabetics does. So I'm sure you've all experienced that the amount of heat that is being generated by components, be it chips or battery packs, increases every year, making it more and more challenging to meet the thermal requirement. So thermal engineers are struggling, I would say, a harder time to meet or to find designs that meet the performance requirements. And that's where we come in. So the whole idea behind Diabetics, or the founders of Diabetics, worked on smart algorithms to improve or to streamline that design process. And now we make those smart algorithms available for any engineer. So by using those, your output is very much increased, as well as the time that you have to spend on a given application is very much reduced. On top right, you see ANSYS and Hexagon, two of the biggest names within the CFD world. Both of them have acknowledged the strength of our software, have reached out to us, and we made them our technology partners. But that's enough about Diabetics. Let's move on to the real topic of today's webinar, which is of course the thermal management early on in the design cycle. I've written down here some points of why early thermal management is important. So first of all, of course, performance and reliability. Usually, the thermal aspect is tackled towards the end. So, for example, if we have a look at the electronics industry, the engineers focus mainly on the functionality of the device, so placing the chips on the PCB to boost or to maximize the functionality of the device itself, and only then do they tackle the thermal challenge. But that's not the best way of tackling it, because it might be that even though the performance in theory of the device is incredibly good, it might be that the heat that's being generated by the component is just too much, or will cause for throttling of the chips themselves. In the automotive industry, for battery packs, if you don't manage or if you don't meet the thermal requirements, you'll get thermal runaway, and there are plenty of news articles that show the catastrophic results of that. So that's why tackling that thermal management early on will increase performance and reliability of those designs. Secondly, cost and resource efficiency. If you only tackle thermal management at the end, or if you only consider thermal management towards the end, as I mentioned, it might be that you find a design, or if you design something that simply cannot meet the thermal requirements. That means that you have to redesign that component, which of course has a very high cost related to it, as well as the engineers that have to spend time on it have to redo most of the work. By tackling thermal management early on in the design cycle, so we basically optimize the performance of the device itself as well as the thermal performance. So in the end, you have a more well-rounded final product. As I highlighted, or as I hinted towards with thermal runaway in the automotive industry, by tackling thermal management early on, you improve the safety and as a consequence, the user experience. There are quite a bit of regulatory compliances specific to thermal management. So by tackling that early on, it's easier to meet those thermal requirements. And it's of course more sustainable and energy efficient if your device meets all the thermal requirements, that basically it doesn't burn out after a couple of uses. How can you tackle thermal management? So there are a couple of ways. The first way is the conventional way of working. Let's say I'll mainly discuss a chip layout, but you have a certain chip layout on your PCB, and below it you have some free space to design a heatsink. The first way of tackling it would be to create a CAD model. For example, draw some pins or fins, or if you have some experience with heatsinks, draw your own heatsink design. You can then run CFD simulations or do some back of the envelope calculations, after which you have to post-process the results, analyze the results, and you loop through this until you get a solution. What I propose doing is to use a generative design. The input is exactly the same, so if you're given chip layout, given PCB and a heatsink, an empty heatsink space below, and in the first step you can run it in concept generator mode, which gives you a wide variety of different concepts, 100, 1000, even more, and those concepts can be generated in a very fast manner. What is the benefit of this? You get great insight into what design change affects the performance and how far the performance is from the thermal requirements. For example, if the performance is way above the thermal requirements, then you know that the chip layout, for example, is not sufficient and you have to redesign it. If the thermal performance is way below the requirements, it means that you have a bit of room to play with. For example, that you can condense everything or package it in a tighter space. And if you're right around the edge, then of course you know you're on the edge of the performance. So don't make too many design changes anymore. So there's the concept generator stage, and with generative design, you can then move on if the performance is not sufficient yet. For example, just above the thermal requirements, you can then move on to further optimization. For example, you use one of those concepts to push the software in a certain direction and to speed up the optimization stage to a final optimal solution. For today's webinar, I will mainly cover the first half, of course, the concept generator stage, where you get, as I mentioned, a wide variety of different applications, and in our software there is a very nice interface to give you insight into what design change affects the performance, as well as what design was attempted for each iteration. But more on that later on. You might think to yourself, isn't this very difficult? Do I need some experience, or do I need a lot of knowledge, CFD knowledge, to work with the software? Not at all. You only have to follow 4 somewhat simple steps. In the first step, you upload your geometry. So basically, you upload the geometry with your heat sources, your chips, your PCB, and the empty heatsink space below. Then you set the solids and the fluids. So you basically dictate: is aluminum being used? Is copper being used? Is it liquid cooled, air cooled? That's something that is specified here. Next, you set the boundary conditions. So your inlet condition, for example, a fan or a pump, as well as your heat source. So how much heat do the chips actually produce? And lastly, you have to specify Colsim with a design domain. There's the volume where Colsim can basically change or create those concepts. And you have to let Colsim know what to optimize for, and those are the targets. Most likely heat exchange efficiency maximization, or it might be weight minimization, or the equivalent constraints. Colsim has 20 plus targets that you can mix and match however you see fit. And that's it. So once you complete all 4 steps, Colsim knows enough, and it will start computing and output those concepts to you. Colsim takes manufacturability into account from the start. So as a user, you can dictate what kind of structures Colsim can consider. For example, in the early design phase for purely prototyping, you can, for example, ask Colsim to generate 3D printed or CNC designs. Or if it's for mass manufacturing, then you can ask Colsim to generate structures using the die casting or sheet metal forming constraints. And for each technique, you have full control over the settings that govern the technique. So whatever, by modifying those parameters, by changing those parameters, you ensure that whatever Colsim outputs will meet your manufacturing capabilities. So those designs can be actually produced. All right, that's enough about the theory, I would say, and the introduction. Let's now apply it into practice by considering a double-sided power inverter as well as an LED lighting application. The reason why I chose 2 applications is the double-sided power inverter is a liquid-cooled application, or first convection application, sorry, while the LED lighting application is natural convection. So that I can show you the subtle differences between these 2 types of applications. But both use aluminum, so it's quite cheap material with a very good conductivity. The forced convection case, the liquid cooled application, has of course more heat compared to the LED application. In the liquid cooled application, we will consider 3D printable concepts like linoids and gyroids, while for the natural convection case, we'll consider for mass manufacturing using die casting, where we consider pins and fins as the concepts to optimize. Alright, let's now switch to our favorite generative design software called Gulfstream. Yes. So once you log on to the platform, you will be treated with the project overview, as the name implies. It gives an overview of all the different projects to keep everything as organized as possible. Let's first move on to our first application, the power inverter. Inside of your project folder, you can then create as many cases as you would like. But for the concept generator, we will of course create a standard design case, or what we call a standard design case. As you remember from the slide deck, once you create a new case, Gulfstream will ask you to upload a step file. I will skip that part and move straight to a case that already has a geometry. Yes. And once you move to the geometry, you can basically then click on each of the entities and fill in the information. So you have an interactive GUI here in the middle and your regions tree on the left. And all the entities that you see here are predefined in my CAD environment. To explain a bit the application, so we have 90 chips in total, 45 on the top, 45 on the bottom, and all of them produce the same amount of heat. They are placed on copper heat spreaders. These copper heat spreaders sandwich a cover and a housing And then we have, of course, our coolant in between. So starting with the cover, Colson will ask you whether or not it's solid or fluid. In this case, of course, it is a solid. And then you can ask Colson, you can let Colson know out of what material it is made. For example, if it's copper, you can search for it, and there are some coppers available for you to select. But for this application, as I mentioned, it is aluminum, or the 6061 version of aluminum alloy. And that's sufficient. Everything below is optional. For example, if it were transparent, you can enable radiation. If the cover, for whatever reason, produces some heat, you can add it as a source. Or if it rotates, you can add rotation. But none of these are applicable here, so I will leave them blank. Same for the housing. It's a solid made out of aluminum. I will quickly change that. This one, yes. And our copper heat sparers, again, that's a solid made out of copper, of course, now. For chips, we simplify the geometry a bit. We will assume that all the heat will come in uniformly through the interface with the copper heat sparers. So we omitted the chips themselves and replaced them by binder conditions. And again, from the drop-down, you can then specify what type of binder condition you want to impose. Fix the temperature, fix the heat that is being produced. Is it an external wall where you have convection towards the environment? Is it insulated, or is there some periodicity? Then you can use a cyclic binder condition. But in this case, it's a heated wall. All of those chips produce heat. We can then specify how much heat is being generated by all of those chips combined. So a little over 4 kilowatts of energy. I'll come back to the targets later. Then we have our coolant, which of course of type fluid now. And again, Colson will ask you to specify what type of coolant will be used. Is it air? Is it a water glycol mixture? And if it's so, what mixture rate is being used? 40-60, 50-50, or some other mixture rate? Entirely up to you to configure that. Here we'll use water glycol with a 40-60 mixture rate. And then you have control over what kind of terminals model will be used. If it's a laminar case, of course use laminar. If it's a turbulent case, you can choose which terminals model you want to go for. Again, that is all sufficient for Colson to start working with. Here we have a forced convection case with a single inlet and a single outlet. So I provided some binder conditions. And again, from the drop-down, you select what type of binder condition you want to impose. Do you want to fix a fluid that comes in? Is it a certain pressure at the inlet? Or do you want to use a pump or a fan at the inlet? Again, entirely up to you how you want to configure those. For this application, I just chose a fixed fluid inlet, where I specify given volumetric flow rate. If you want, you can change it to velocity or mass flow rate. And I provide, or this amount of flow enters through that inlet patch at 40 degrees inlet temperature. What goes in must go out, of course. So let's move on to the outlet. And here again, you have a wide variety of different outlet conditions that you can choose from. Be it a pressure outlet, or a pump or a fan outlet. Entirely up to you what you want to do there. Alright, so we have solids, fluids, and their boundary conditions. We can then move on to the design domain. And the design domain, as I mentioned, dictates what kind of cooling structures, or where the volume where Colson can change those, where it can generate those concepts. And here, I'll deselect a few to make it a bit more clear. From the pop-up window, you can then dictate what kind of cooling structures Colson can consider. In this case, we want to consider 3D printing. Are we allowed for 3D printing? So do you want to consider gyroids, Schwartz elements, diamonds, Neovius, split P, or lidonoids? Entirely up to you here what you want to do. Simply select it, or select a few, and save. and then you specify the settings that govern 3D printing. So your printing resolution, your overhang angle. And lastly, you specify out of what material those gyroids or linoids are made out of. And here that is aluminum again. Yes. And I will deselect. I will only want to consider aluminum. Okay. So that's all the information that I have to provide here. The last thing we have to let CoSim know is what to optimize for, and that's where the targets come in. I have one target here on the inlet and one target on the chips. On the inlet, given that I've fixed the flow rate, I of course don't want the pressure drop to rise to infinitely high, so I put a constraint. If you want, you can also minimize the pressure drop if you so desire. But here I chose for the constraint, so I let CoSim know whatever concepts that are generated within the design domain, the pressure drop can never exceed 60 kilopascal in this example. Then our chips, our heat producing component, of course. Here we want to maximize the heat exchange efficiency, or equivalently minimize the temperatures. And you can add on, can keep on adding additional objectives if you so desire. For example, if thermal uniformity is also important, you can add an additional objective. But it's early thermal management, so let's just consider the temperature minimization objective. And that's it. So we have our solids, fluids, boundary conditions, the design domain, and the targets. That's sufficient for CoSim to start computing. And once CoSim is ready, or once CoSim is running as well, it will output all of its intermediate data points for you to have a look at. For example, here, if you go to our gyroids concepts, I can see that CoSim outputted 100 different designs. And if I go to the design evolution tab, we can then have a look at what the performance, how the different concepts correspond, or how they correlate to one another. The first image that you're treated with is the overall design performance graph. So basically that means the lower the value, the better the performance. It's always an optimization. With an optimization, the lower the value, the better, of course. And on the x-axis, you have your different iterations. So by default, the first iteration, the first design is selected. But if you want to have a look, for example, at this iteration, you simply click on it and it will update. The dots can be any of 3 colors. Red means it's infeasible. For example, if our pressure drop constraint were to be exceeded, that's an infeasible design. Luckily, all the designs here meet the pressure drop constraint, so they are all feasible. Blue means the design is feasible, but at this point it's not the best one. And green means at this point is the best design. So you have to look at the overall design performance graph as a timeline. CoSim, when it made the first iteration available, only knows that iteration. It was feasible, hence it's a green design, because it's the only design that it can compare to. The second design is slightly worse, hence it's blue, but it's still feasible. And then anytime it improved on the previous green design, it's made that design green. So the last green dot, this one, the 95th design, is the best design out of all the attempts that CoSim made. If you scroll down below, you can then have a look at what geometry CoSim attempted. So here it's 19 different gyroids with these dimensions that were being generated. If you scroll down further, you will see the individual targets. So we have a pressure loss constraint. This group of iterations, or this group of designs, were very close to the constraint, but didn't exceed it. And our temperature minimization, of course, that's the temperature of the chips, how they correlate to one another. And for the keen-eyed viewers, this graph is identical to this one. In the interest of time, I will skip the lienoids and move on to the natural convection case. Natural convection LED, yes. So here, similar as before, you create a new geometry. You create a new case, upload a geometry, and fill in all the information. It's a very simple LED. Yes. So we have our LED itself that produces 10 watts of energy, made out of gallium arsenide. Of course, here again we want to minimize the temperature. It's fixed to a supporting plate made out of aluminum, and then we have some glass to protect the LED and to disperse the light a bit. And then we have a big air domain surrounding the LED to help cool it down, with a heatsink right on top of it. So what is the change in input? Here is a natural convection case. So for the air domain, we enable buoyancy. Or I can then specify what the atmospheric conditions are, so the atmospheric pressure drop and the atmospheric temperature, and in what direction the gravitational vector is pointing. So on the bottom left here, you see the coordinate system, where the red arrow means X, the yellow arrow means Y, and the green arrow means it's Z. And our LED is positioned like this, so our gravitational vector is along positive Z. Hence why I provided here the positive Z. Everything else is exactly the same as before. For this case, I only considered die-casted designs, circles and rectangles, which again, given set of manufacturing settings, and I have asked Colson to optimize those. So let's have a look at our fins. In this case, Colson only outputted 97 different iterations, but you'll be treated with again the same screen. If you go to the Design Evolution tab, you have a history of all the designs that Colson attempted and how the performance compares to one another. And if you move on to the best design, we can see that it's only three fins, rectangular fins, that are considered with these dimensions. And if you want to extract this, you can of course download it either in step file, 3MF or STL file format. Okay, we are rapidly approaching the 30-minute mark, so unfortunately I will have to skip the Q&A session, and I will move on straight to, if you want to try Colson for your own, there is a viewer. You can apply for a viewer access, so you can have a look at finished demos, what the input is, what the results are. You can even download those results and analyze them in more detail. And to request access, you can simply navigate to our Diabetics website and then click on the Try Now button. If you have any further questions, or if you want to sit together to discuss your applications in more detail, feel free to contact the team either by emailing to info@diabetics.com or by calling this phone number. I thank you all very much for your time. I hope it was interesting, and I wish you all a very pleasant day still. Hope to see you later. Bye bye.